Valve siphons, the no pollution solution to the glacial lake outburst flood problem. The danger of a glacial lake outburst flood has caused much concern among the Himalayan nations and states for many years. Now it appears that global warming or climate change is accelerating in the polar regions, including the third pole, the Himalayas. The purpose of this video is to provide information about a possible solution to the G.L.O.F problem, using fairly large siphons constructed from PVC or similar materials. Valve siphons have two valves, one each on the intake and outflow ends, and a sealable filling port at the high point of the assembly. The assembly creates a gravitational geometric imbalance in a static state. After the siphon is fully primed, the valves are opened in the proper sequence, resulting in a continuous flow. After the valves are opened, there are no moving parts, no fuel required, and no pollution. The siphons will be in place for weeks or months, but the visual impact on the environment can be almost negated by simply covering the operating assembly with dirt or other natural cover, leaving only a sound of running water. A valve siphon will continue to operate until the water level at the intake becomes too low, creating a whirlpool which will eventually allow too much air into the system. At assembly, the intake should be placed at least 10 meters below water level if possible, ensuring that the system will continue to operate until the desired water level has been attained. My name is E.J. Long. I'm a member of the International Union of Operating Engineers here in Alaska. And I've worked on some large projects, including draining large amounts of water from man-made lakes. Of course, the glacial lakes will be much larger, but the siphons will operate as long as you need them to. The largest project I've drained was about 25 million liters, and using two 100 millimeter siphons, we were able to drain that pond in just about 5 days. This is a small model of a valve siphon. All valve siphons have an intake valve, a sealable filling port at the high point of the assembly, and an outlet valve down at the bottom. This is the outlet valve, the downhill leg, you might say. This is the filling port at the high point of the assembly, and then there is the inlet valve. This is a 200-liter tank. Let's just try to imagine that this represents a glacial lake. And the valve siphon is in here. This bottom section here needs to be about 12 meters long. That way you can lower the water level by 7 liters before the siphon starts to develop a whirlpool. These ping pong balls are in here to make it easier to see the water level as the water level drops. To start the siphon, first make sure that the intake valve is below water level and open it. This way you can make sure that there's no air in the priming section. So first thing we'll do is make sure it's got water all the way past the valve, and then close the intake valve. Next we make sure that the outlet valve is closed. When they're in line with the pipe, the valve is open. Here it's closed and ready to fill. Now that this valve is closed and the outlet valve is closed, this part's primed. Now we open up the fill port, fill it with water. Now here I'm just using a hose, but on location you can simply use buckets of water to fill the assembly. It's going to take a few minutes because the assemblies will be quite large, but there are no pumps required, no type of machinery, electricity, nothing. This is all done by hand. Now that the assembly is full and all the air has been tapped out, we'll go ahead and put the plug in. Now with the large assemblies we'll be using thread tape, but for this demonstration it's really not necessary. This is a very low power siphon compared to the ones we'll see in the field. Okay, to start your siphon, first you open the outlet valve, and usually there'd be two people, but for this there's just me. Then you open the intake valve, and the system is flowing. Once it's been turned on, the inlet valve can remain open. The suction of the water inside the longer downhill leg will maintain a negative pressure on the water in here. It won't drain out. Once your siphon's been primed and started, just leave it running. And it'll run for weeks or months. And here we can see the water being drained from this tank. This is a very small siphon, but it operates at about 200 liters per minute. That adds up day after day, week after week. When the water level gets to the desired level, you can just turn it off, or maybe just have it on at a reduced flow in order to maintain the desired water level in the lakes. In any event, the siphon will remain primed and ready to flow. Once it's primed, as long as there's no air in the system, the siphon's ready to go. No electricity, no fuel, no pollution, no maintenance. Okay. As we mentioned earlier, the starting sequence, you open the outflow valve first and then the intake valve. Now with the small demonstrator model that we showed, there isn't much of a time delay, but with a very large siphon there's a significant time delay. Here's your siphon when it's filled with water and ready to start. The gravity is affecting both sides, pulling the water either direction. Now as you open the outflow valve, the water will gurgle out, and as it's gurgling out, it's exerting a negative pressure, sort of a suction, on the rest of the water that's in the pipe. And this suction area will travel back until it gets to your intake valve, and it may take some time. And when it gets there, there will be a noticeable sound, kind of a thunk sound, and then you know that it's time to open the valve. Once they're both open, then you'll get full flow. The largest siphons I've built were 100 millimeter by about 30 meters in length, and the time delay on that siphon was over 5 seconds. So with your longer siphons, be prepared to wait until you hear that sound. Then you'll know that the suction has traveled all the way to the end and the pipe will flow. The siphons that you need for the glacial lakes will be larger dimension. This is a 100 millimeter PVC pipe. Typically they are 6 meters in length. Your PVC pipe comes in different thicknesses, and the most common are called Schedule 40 and Schedule 80. The Schedule 40 is what you want. It's thinner, but it's plenty strong. Schedule 80, thicker and stronger. The main reason that you want to use Schedule 40 is because it's much lighter in weight. Schedule 80 would be very difficult to carry for a long ways. Also, the Schedule 40 is more flexible, which may be important. Schedule 40 is less expensive and more common. Schedule 80 is more expensive and less available. So be sure to watch out for that. Also, the fittings are specific to the pipe thickness, because these pipes are measured by the inside diameter. So make sure that you get fittings that are for Schedule 40. You can try them on the pipe before you transport them a long ways. This is the fill port. You can see it's much larger. This is the elbow. You may or may not be using elbows. It depends on the topography of the location. Another fitting you may need to use if you're dealing with cut pipes are called couplers. This is the type that you glue them together. This type here is flexible with collars on it. Now when the fill port is ready to be sealed, here's your plug. You want a good seal, so you use something called thread tape or Teflon tape. Simply wind it on here in the direction of the thread. Pull tightly. Whoops. Well, not too tightly. Just put it on here so that it fills the gaps in the thread. You don't need too much. And you just put it like that and screw it in. And when it's tightened in, it'll make a really good seal. You need to have a good seal so that there's no air allowed into the system. Here we can see how much larger the ball valve will need to be. That's a 100 millimeter ball valve. These 4-inch ball valves are very strong, and so they're kind of stiff. It'll be easier to get more leverage on if the valve is located at a horizontal rather than vertical point. So when it's time to open it, use a wrench or maybe a big piece of pipe to give you more leverage, and it's ready to flow. And if you want to turn it off, like so. The majority of the assembly in the field will be joining longer pieces of pipe together. Before you do that, you want to make sure that they're clean. It doesn't have to be perfect, but you want to make sure you get a good seal with no dirt in the area that's to be attached. And in order to ensure that there's no pollution or drips of any kind, you can just use cardboard just in case. Now the adhesive is a two-part material. You've got the primer, which you want to just apply to the pipe on both sides. And also on the inner part, the bell. Once the primer is on there, it's going to help the glue work better and provide a good seal. And this is the adhesive. It'll be easier with two people because these pipes are going to be kind of long and unwieldy. Get it on both surfaces, first the primer and then the adhesive. It takes a few minutes to dry, but you don't need to wait for it to dry to fit it together. Just like that. There's really no dripping, but again, if you use a piece of cardboard, there won't be any pollution whatsoever. And these just need to cure for a few minutes, so as you assemble the pipe, the assembly will stay together just fine. And when it's time to fill it with water, everything should be at full strength and ready to provide a good seal and work for weeks or months without any problems. No further maintenance required. And no electric power tools or any other kind of tools are required other than a saw. You can use a hand saw. There may be some times when you'll need to shorten a piece of pipe. And the whole assembly should just take a few hours. Once it's completed and filled, it should run indefinitely. The siphon demonstration that you've just seen works with this type of a shape, of course, many times a glacial lake won't have a perfect shape like this. It may be more rounded, where you won't even need elbows. As long as there's a high point in the system where you can fill it, that way you'll be able to get all the air out of the system, and when the valves are open in proper sequence, the siphon will flow. Some of the factors that affect the rate of flow in these valve siphons are listed here. One is the ratio of the intake leg to the outflow leg. The outflow leg should be at least 3 times longer in order to provide a good suction. Another one is the steepness of the leg angles. Another one, the straightness of the legs, the elevation of the lake, and the diameter of the pipe. It's all very simple, but I'll just go through it quickly. The ratio can be more easily understood by assuming that you were just balancing these pipes on a point, a fulcrum here. The intake leg is shorter, the outflow leg is longer. The water that's inside the pipe is going to make the pipe heavier on this side. When the pipe's not moving, the heavy water is going to pull this water through the pipe. More water creates an imbalance, and what makes them work is the molecular cohesion of water. And we're just using the natural properties of water to help to drain these lakes. We don't need machinery for this. Another factor affecting the flow is the steepness of the legs. Certainly if the leg is steeper, the water is going to want to flow faster. So that will depend on the topography, the local terrain. Each lake will be different. But the steeper outflow angle adds the gravity assist for more velocity or more flow. In some cases you may need to run the outflow leg a little further in order to take advantage of a steeper section of the terrain. That will give you more flow. And another thing that's really quite simple, but the straighter the legs are, the better the water will flow. The intake length should be minimized, of course, but any bends in the pipe will create friction, and that will slow the water down. So you want to try to keep the legs as straight as possible. And as far as sideways turns, again, just try to keep it as straight as possible. Obviously, an important factor to be considered with the glacial lakes is the high elevation where they are located. The higher you get, the properties of water change slightly. So at a higher elevation, the molecular cohesion of the water is slightly reduced because of the reduced atmospheric pressure. Also, believe it or not, gravity is slightly less the higher the elevation. It shouldn't be a big factor, but it's just something to consider. And also at the very high elevations, if you have freezing conditions in wintertime, it's probably best to just go ahead and empty the water out of the siphon and then start it up again the following spring. To empty the water from a siphon, simply loosen the plug at the high point where you filled it with water. That will allow air into the siphon and it'll drain out both sides, and you won't have to worry about freezing, damaging the pipes. Another factor that affects the flow of the pipe is the pipe diameter. In this case, I think 100 millimeters would be best. You can get larger pipe, but it becomes much more expensive and more difficult to handle. Also, if you get too much water flow, then you'll have to deal with erosion where the water comes out. I would expect that you should be able to achieve a flow rate of around 3,000 to 4,000 liters per minute with a 100 millimeter siphon. And that's enough to just create a nice stream that's easy to deal with. You don't have to worry about flooding problems or other issues. As I mentioned, a 100 millimeter siphon should produce a flow rate of around 4,000 liters per minute. That means 6 million liters per day. So these siphons will operate for several weeks or longer. Even though these are very large lakes, in many cases you'll be able to notice that the water levels are dropping very soon. Once the water level is where you want it to be, you can either turn the siphon off or maybe just turn the flow rate down by adjusting the output valve. Of course, if you want, you can just remove the siphon altogether and reuse it in another lake. These are completely recyclable. The valve siphons will also provide a steady stream of water which may be used to generate hydroelectric power or for agricultural purposes. And I'd like to talk for just a minute about some of the logistics you may face. I realize the terrain is very difficult and it may take several days to reach the work area. But I believe the community can be involved, and I think that's probably a good way to go. The transportation of the pipes to the project could provide some employment for local residents if desired. It would seem reasonable to expect that a person can carry one piece of pipe at a time, as they're not particularly heavy, but will be somewhat of a challenge at 6 meters in length. After assembly, which should only take a few hours, the same helpers could assist in covering the siphon with dirt if desired. When the siphon is started, it may be advisable to help direct the stream of water toward the nearest creek or river. And upon their return to their communities, these same workers would be able to explain the situation to their neighbors so they won't be too concerned about the sudden appearance of a new stream of water. The PVC pipes and fittings should be available from local manufacturers, although I've been unable to get cost estimates on the internet from India. Here in Anchorage, where costs are quite high, a 100-meter siphon would cost about $2,000. Once a siphon is operational, there should be no further expenditure as no maintenance is required. A siphon should continue to operate until you turn it off. However, it's possible that something may become lodged in the intake end of the pipe because there's a lot of suction there. I don't know if it would be maybe a rock or maybe some dirt or some ice. I'm not sure what it might be, but there's a possibility that something could impede the flow. And that's why the intake end of the pipe can be slightly modified as shown in the photo. This way, if the pipe is blocked, the extra holes will allow the water to continue to flow through. I hope this information is helpful to you. We'd all like to see this problem solved, and it can be done easily and inexpensively and with no pollution whatsoever. If you have any questions or comments, feel free to contact me. There's my email address, and you can text me at this number. I believe the water levels in the dangerous glacial lakes can be safely lowered using valve siphons. I encourage you to build a small demonstrator model so that you can see how well the system works. It will certainly work very well on a large scale also. Thank you. Valve siphons, the no pollution solution to the glacial lake outburst flood problem.